We're live. Delbert, thanks for doing it tonight. My honor, appreciate it. Glad to do it. Everybody knows me, Jeff Mattocks. Allied Equipment for how many decades now? 3.3. Okay. Any questions you have on pumps, Jeff can answer for you.
Thank you. If everybody has any questions while we're doing this, just stop me, whatever you need to know. I'm gonna start off pretty basic, and we're gonna go to pump curve, there's other things, so, let's get started. If I'm not working again that time. Well, it's there's something up on the screen. Let's see where it's at. There we go. Okay, so basically to start really easy, these are like a residential circulator. Pico came out with these, are the first ones to do this, back in the early 60s. They replaced these 3-piece pumps. That was the standard for years in residential. They call it 3-piece pump because you have a motor, a bracket assembly, and your balloon, your impeller. These pumps basically do the same thing here. These have a little cartridge inside of them. So when you want to repair these have a mechanical seal. These have an O-ring. There's a little cartridge in here with the impeller built in. When you want to repair these, you pull out the 4 bolts, take off the motor, cartridge goes in the garbage, new cartridge goes in. Much easier to put on. No mechanical seal to fail, no coupling. There's a spring couple in these. So these are becoming much more prevalent. And over the years, they're just building more and more of those. They used to be just a 007, now they go up to a 0013. They're making it bigger and bigger. These are more, this is the cartridges I was talking about for the 00s. We make, they come in stainless for domestic and cast iron for heating. Now there's a big change. These are 006Es. Everybody's going to ECM now, which is basically instead of having a wound synchronous motor, you now have a permanent magnet built into them. And a lot of times when you see these now, a lot of people are having to put in a magnetic separator into their system. And the reason that is this has got a full magnet charge. When these shut off, the magnetism goes away. These are always magnetized. If you have any metal in the system, that's what they want to collect in your pumps. But now we're seeing a lot of magnetic separators being sold in addition to air separators. This is also the new range. These are all new ECM pumps. Same concept here. They're ECM. You can run them on a 0 to 10 volt signal. You don't need a VFD. You can actually run these. They can run self-sensing, 0 to 10, bunch of different features. We make the 00s like this too, and these, some of them have their own little dongle that comes with it to set them, and you can do it remotely. So anyhow, this is just the new ranges, the ECM. They're much more energy efficient is the reason for them. Then you get a little bit bigger commercial. We get in, these are our 1900 Telengosses would be a Series 60 and a Series 90. The 1600 actually has a coupling in here, motor. It's like a 3-piece circulator, but much larger. They go up to about 3 horse. And this is the exact same volute, except instead of having a bearing assembly in here, we're direct driven right from the impeller to the motor. So you don't have you have a seal kit, but no bearing assembly. These have to be mounted this way. If it says horizontal, that means this is parallel to the ground. It has to be mounted that way. You can't flip it up on end. These can go either way. That's the benefit of them. And then we can also get these with the VFD actually built in right from the factory. So if you need a VFD application, they come with it. Yes, sir.
Any significant of the paint color, green versus red, or
green's much easier on the eye. It's much better. It lasts longer than the red. So
That's institutional green.
Yeah, it's nice and easy on the eyes.
50s and 60s.
It's my favorite color. Matches money. I mean, you like money, don't you?
it matches mine.
These are the bigger pumps now as we go up in size. These are the F5 pumps. This is a base mounted end suction pump, they call it. The reason they call that, the flow actually comes in here and turns 90 degrees and goes out of the pump. These also come with an SFI. We can send them with a match VFD. This is the exact same pump as this, except this has a flex coupler and a remote motor. This pump here is actually coupled right to, it's a JM shaft motor, and it's actually tied right to the impeller. The advantage of these, if I blow a motor here, this one I have to crack and open the water side. I'm not gonna get wet. This one, if I blow a motor, I break the coupling, I have to pick the motor up. Space saving, versus easier for maintenance. So these can actually be mounted up on their nose. These are just space saving versus this, but this is the workhorse. This is probably 80% of what we sell is this one right here. And Goss and Armstrong, everybody makes a similar pump. This isn't proprietary. Yes. This is called a KV pump. This is a KS pump. These are just larger vertical inline pumps. These is direct driven, just like the 1900 series were. This is split coupled. Same pump, same impeller, different motor. And again, this one I have to break the wet side to fix it. These go all the way up to about 150 horse on these now, 14 by 14. And if you need to replace the motor, you can lift the motor off and not have to break the water side. And we make these with an internal and an external seal. So, yes, sir.
So why would anyone go with the one that you have to open the wet side to service it when you can go?
Cost. This is significantly more money because of the coupler. This is down, just cheaper. And the inline pumps do about what the F5s do. And they just are space saving. And then here we also make these, they come like this from the factory with an I'll get into the SKB with the self-sensing. We actually mount the drives right to the pumps. This is exactly how it comes from the factory. When the flows go up, now we get into what we call our CA. This is called a double suction horizontal split pump. Same as the FI, we have a motor, coupling, and then we have our pump assembly. The difference is on the FI pump, when the water comes in here, it comes in, hits the eye of the impeller. When you pipe one of these, and I'll get into suction diffusers in a second, you need 8 to 10 equivalent pipe diameters coming into this pump. The reason being, if I make a 90 and turn right in here without a suction diffuser, the water is very turbulent. It can cause the pump to malform. So, like I said, you just said this is a single suction, in, out. We go to the TA pumps. What happens here is the water comes in this way, actually comes in here and goes around both sides. There's an eye of the impeller on each side of that impeller. It's open on both sides. So it's coming in double suction, and then it gets thrown out and goes out to discharge. This is just the next size. These are TAs. The bigger we get, these are the GTs. Much bigger horizontal splits. And then we make Mattocks that makes these two. These are the gravity or space saving, and these are the angle type gravity pumps, TSCs. The problem is that these are very hard to work on, very labor intensive, and super expensive. These we don't see a lot of because these are twice what these are. Very expensive. This is a vertical turbine pump. The way these work, you would mount this on a base plate. This would actually hang down in the sump. These are used a lot on cooling towers. We've got a sump right underneath. The tower returns right back to the sump. This spins. The water, these are impellers. I can keep stacking these impellers. I can have a single, 2, 3. There's a strainer here. The more impellers I stack is just like putting pumps in series. I can, 1,000 GPM at 20 feet ahead, plus 20 feet ahead, plus 20 feet ahead, plus 20 feet ahead. I go way up in pressure. So it's like pumps in line. And there's just a big shaft here with spider couplings. The impellers sit in here and turn, feed each other. The water comes out and goes out to the system. These are vertical, typically they're hollow shaft motors. There's a shaft that actually slides down into here and ties into the pump. So if you need to take the motor off, you can take this coupling off, pull the shaft and take the motor off. This is a more residential.
A keyed hollow shaft or?
Yeah, what it is up in here, they actually have there's a coupling down here, it's got a vent with it. The shaft will actually be down on the ground. When you set these up, you take the shaft up here and you spin it, get it to lock, you go face to face. Then you tie in a glib key on the top. There's a slot, there's a groove in the shaft with a glib key that goes in. Now I'm locked. And these usually have an NRR ratchet, which is a non-reversing ratchet. It can only spin one way. If you spin these the wrong way, they'll chew themselves up. But it can only go one way. They're very noisy when they start. There's ball bearings that fall in a hole. And when they start it, centrifugal force throws the bearings out. There's literally ball bearings that go up a race. And then as it slows down, you hear the ball bearing tick, 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 and they'll finally drop in a hole.
Like roulette.
That's what the centrifugal force forces them one way or the other way locks them. So once you do that, once you tie this in, there's lid keys in here, there's a nut up here. And then you take the nut and start turning the nut, and it'll actually lift the impellers in here slightly into the housing to their center. Now they're hanging suspended, it spins freely. When they're not hooked, they're down on the bottom. You can't turn that shaft. As I pull that nut up, pull that shaft, they'll start spinning. We go to their free, and then you put a lock key.
Or is it pre-measured for you and just?
Well, you just go till they spin free. If they're enclosed impeller, you just raise them till they spin with no resistance. And then you there's a little lock screw on the top that locks that into place. But these are for really high flows, especially if you've got a lot of high head. Yes, sir.
Is that for like when the cooling tower is on the ground and you got a tall building?
Right, exactly. And we can put the sump down below. And the big concrete sump, 10,000 gallon sump right in the ground. These will have a mount right on top of the sump, and there's a big hole cut into the sump, and they'll just drop these right down into the sump, and they'll bolt on this base plate, and they just pipe them right there. Yes, sir.
Use these for sewage too?
They do, yeah, they can be used for sewage, but most time in sewage, I'm not really gonna touch on a lot of sewage tonight, that's a whole nother story, but typically HVAC, these are enclosed impellers. Sewage usually has an open impeller, so if you get any strings or any garbage in there, they don't clog up the impeller. Yeah. So that's a good time to show this too. This is an impeller out of a standard FI pump. And what you have here, this is called an enclosed impeller. And the reason it's enclosed, you see that these are on both sides. There's an open impeller, picture this piece on, it would just have the veins. So this can get clogged, but the open veins can't. This is called the eye. Remember that end suction pump? I told you the flow's coming in. The flow is going to come right in here. This is called a Francis vein impeller. The water goes in here. As this turns, you'll see that these are curved. These are actually curved in here like this. And as it spins, the water gets forced with that spin up to the cut water of the pump, which is the port of the pump here. As it spins, it forces the water up and out. You can see in here they're curved. You'll see what and it spins. You don't want to bite into the water. You ever have to figure out the rotation? You want to backhand it, not bite in.
They're not cups that throw water down the pipe.
Let's say exactly. And these are trimmed. It says 8.8. We can trim impellers. So I'll get into that in a minute. These are typically bronze, can be stainless, iron. There's all sorts of different applications. Now you'll see a lot of little marks on here. That's by design. These are balanced, and that's how they balance it in the grinder. Or you'll see drill holes. You see drill holes that didn't have mice didn't get in there. They're actually using that for balance. So I'll pass that around. Somebody wants to look at it. Careful, the edge is kind of sharp. Any questions? And these are what we were talking about. Remember the end suction pumps? I was talking about the 5 to 8 pipe diameters you need. This is called a suction diffuser. If I put this on an end suction pump, I no longer need my 5 to 8 pipe diameters. What this does for you, it shortens that 5 to 8. There's a startup strainer in here, a 20 mesh strainer for startup. There's a 5/8 per strainer in here for pump protection. These are give you your 90. I can reduce 6x4, 6x3. I've got my strainer. It comes with a little foot that goes on here. You put on a piece of pipe, you can jack it up for support. This allows the enter straightening veins in here. If you look inside here, see these veins? When this water comes in and turns 90, that water this gives you that laminar flow we're looking for while we have the 5 to 8 pipe diameters. So to being turbulent, it comes in and this straightens the flow out. And those veins, when you open this, you can pull out. You can replace the veins, you can replace the strainers. Once these are started up, it's very important. After about a month or so, you want to go in and pull these. This is anybody's, not mine, Armstrong, Bellegossett, whoever. They all have this 20 mesh starter screen. It's a very fine screen. Over time, it will disintegrate. So once you get your system cleaned up on your original startup, you want to go in here, open this, pull that screen out and rip that 20 mesh off of there and slide right off. And then put it back together because you don't want it to disintegrate. And what I recommend to do is once you pull that out, take those screens, find a piece of wire and tie it to the valve on top of the pump and hang them there. This will happen eventually. A commissioning agent will come in, somebody goes, the strainers taken out? Well, yes, they were. They're right there in the pump. Everybody can see them. There's no question they were taken out. Just good idea.
I like that.
These are triple duty valves. They come look like this in the factory. It's how we ship them. It's really slick if you want to do like a vertical inline pump, you can put a suction diffuser on one side, put a 90-degree MPV in the other, and come down, go 90 and right back up, save floor space. These are used on any type of pump. This straight valve, all you do is take these 4 bolts, this thing will rotate to 90-degree position. So you buy the straight one, you can put it in either way. And the idea of this is, and every pump on the discharge, you want a balancing valve, a separate pump, check valve, and a shut-off valve. This has all 3. There is an integral check in here. This is your scale for balancing. And it's your 100% bubble type shutoff. So instead of having a wafer check, balancing valve,
You use the same stem as your balancing.
that is it. Actually right here.
Then shut off too.
Correct.
You gotta remember where you had it set.
There's a scale here. You can mark the scale. But when you turn it all the way down, it'll go to shut off, or you can take it back to your balance. There's a little indicator here. You can mark, put the indicator where your balance position is. And then you can just reopen the valve right to that balance position. We make these in 150 pound and 250 PSI 4K pressure valves. Okay, few things on pump fundamentals. Flow is just what it says, GPM, gallons per minute, liters per second. Head is actually the amount of differential the pump generates. On a closed system, most people don't realize. I had so many people call me and they say, you know, I've got a 5-story building, you know, in a closed hydronic loop. All this pump does is overcome friction. Your fill pressure fills the loop. You get a 1 or 2 PSI on the top floor. And this pump is just given enough to take the friction. I don't have to lift 5 stories. Now, if the domestic water booster system where I have an open tap, now I have to worry about the lift. But in a closed loop hydronics, don't ever worry about the lift. It's closed, your fill pressure, you set your fill pressure, take the elevation, if it's 23 feet, divide by 2.31, it's 10 PSI at a pound. That's your fill pressure. That'll give you positive pressure on the top. And then your pump will take over from there. Because it's equilibrium on both sides. When it comes up, pushing down. Any questions on that? We'll get into net positive suction head in a little bit. System resistance we talked about, that's what these pumps are doing. Specific gravity is typically 1 for water. You can go to more viscous fluids.
Like glycol.
Like glycol. However, in our experience, if you have anything less, 50% or less than glycol, it's almost negligible. Yes, there's an effect, but people typically oversize pumps 20 to 30%. Glycol, I've done a million calculations at 40%, and it comes out to about 3% on flow, 4.5% on head, and maybe 7% on horsepower. But usually they're so oversized, it's negligible. Once you hit that 50% mark, then it starts making a big difference. Then you really got to start looking at the viscosity and how your pumps account for specific gravity.
That's because it's like thicker or what?
Yes, it's more viscous, so it takes more energy to push it.
More viscous?
Viscous, it's thicker. It's like syrup, you know, like try to pump molasses versus water, you know.
You end up with a little bit less flow and a little bit more amps.
And then more horsepower. So we'll get into that in a
That
second.
could be like 100% outside. So, if the boilers fail and you have 100% outside air or 0, you're gonna freeze it.
That's why they use the glycol.
Like,
And usually we use around here 40% is typical. Snow melting is 40% glycol. And then you have propylene and ethylene. Propylene is safe. Drink or it's in your deodorant and everything. Ethylene will kill you dead.
You still got.
So typically, like snow melt, we always use propylene.
What are you supposed to do?
Okay, this is a pump curve. Everybody seen one of these before?
Like ice cream.
Very simple. This is our flow for any pump. These are all generated by a factory on every pump you select. This is your head in feet. You can get them in meters or liters per second, but this is English. So, and basically, this you see a little dot there. That's your operating point. And what you have in the curves, you got flow, head. These are your impeller cuts. These curvy lines going like this. Those are my impeller trims. Like that one there says 8.0 inches. You know, here I have 10.59759. The lower I trim this, the less head I can get out of the pump. But if I put this impeller, and we'll get to this in a minute, and I'm pumping down here, I'm pumping a lot of horsepower I don't need. On every curve, you see these little lines, 5 horse, 7.5, 10, and 15. So this pump here, you can see this curve doesn't touch this line, so this is a good selection for 7.5 horsepower. Okay, if I put a 5 horse in here and I'm running out here, I'm gonna trip that motor right now. I don't have the horsepower to do it. So you have to look at your impeller curves, and then these lines here are your efficiency points. And basically, that we'll get into the formula in the GPM times 500 times your specific gravity divided by 3960 divided by the efficiency will tell you what your horsepower needs to be. Okay, so you can calculate, that's where this comes from. Any questions on this so far? And each curve, every pump has an RPM. Typically for English or for 560 cycle, you have 1160 RPM, 760 RPM, 3600 RPM. 3600 is 2 poles in the motor, 1750 is 4, 1160 is 4 pole. When I go to 50 hertz, now you go to 1450, they're different RPM, but typically we use 60 hertz here, so you're either going to have an 1160 slows it down and give you less head, quieter pump. 3500, the impellers get smaller, but they're much noisier. Any questions? All right. Oh, I meant to point out one thing here. This thing here, well, this is the system curve right here. And I'm going to get into that in more detail. And all the system curve is telling you, from this duty point, I can calculate this. My system, every system has its own curve. If I throttle the balance valve, I change the curve. And the curve, the pump has to operate. If this point is true, this is exactly where my pump will flow at every GPM. So if I say, okay, right here, I'm at this here, where it's 215 at 70. If I come to 150, it's got to be on the curve. It has to go there. It has to operate on the curve. And we'll get into that in a little more. This is just a curve right here. I showed you the different curves. Like I said, if I have an open system, if I throttle the discharge valve in a pump, this is the beauty of hydronics, or plus or minus 50%. If I over design the pump and I run out here, I can throttle that pump down, add head to the pump, and it's going to move itself back and reduce the flow of that pump. So if I'm overflowing just by choking down the pump, I'm adding head and the curve's going to back up just like this to the flow I want. And I designed for here and I wound up here. If I throttle it, I can get to there. I'm wasting energy. That's why VFDs and stuff are important, but just for the simple concepts. Okay. Here's the laws that I was talking about. These are the affinity laws. These all apply to a fan. They're the same laws. The flow varies directly with the impeller speed. So like I said, 1160 RPM, 1750, they're going to go up proportionally. This is where your pump curve comes from. Your heads varies as a square of the speed. And we'll get into that in a little more because it gets very important. And brake horsepower varies as a cube. Okay. So, if you up your flow 10%, your horsepower is going up to a cube of that. Okay. Any questions? For example, here's how you get this system curve. Remember that affinity law we talked about right here? What part of it? This here, H1N2. If I just divide H2, put a line under here, put H2 here, I have H1 equals N1 over N2 squared divided by H2, right? Then I can go to the curve. If you really want to make this curve, you can go in here and put my first flow in at 450, my head one's at 60, put in my flow 2. I can calculate my second head. Follow me? And I just went to this curve and said, okay, 100 GPM, I know I want 450 at 60. That's my duty point. I'll just go in and pull 100 off here, put in the equation, I get 2.96, I pull out a point right there. I do, okay, let's go to 200. 11.85, I plot a point there. I use the same number, put in 326.67. It's all from that affinity curve with a square, okay? And that's why we have a hyperbolic curve, because it's varying as a square. I can just keep picking numbers and plotting this and draw this in. Now I have my system curve. If this is a true point of my system, my pump can't go anywhere but here. It has to be on that curve. The head varies as a square of the flow. If I'm at 100 GPM, I'm gonna have 2.96 resistance. If I'm at 600, I've got 106 feet of resistance. Okay, make sense? So that's where the system curves come from. Why did I put that one in there? Oh, when you do an open system, like a hydronic booster system, notice all the other, whoops, sorry. Myself. Pushing the wrong button. Normally we start at 0 for a hydronic system because it's a closed loop system. I have no static head. It's all equal. I got 100 pounds on this side. I got 100 pounds on that side. It's equal. In the domestic system, I might start at 26 pounds or 24 pounds, and I'm boosting it up to building 100 pounds. Well, I have to take an account and move this up the curve. I have to add that into my system curve because I'm not starting at 0. I'm starting here at static. Non-overlaid and overloading. This is very important. Okay, a better curve I do here. A lot of people assume this is, let's say this is our operating point. The pump, when you lay in the curve, if this is the true operating point, if I have an 11-inch impeller, the pump's not going to operate here. It's actually operating here because of my larger impeller. I actually, if this is it, and I designed and I missed my design that much, I'm still going to pull this much horsepower, at least 25 horse per run, because this is, the pump has to be on the system curve. The system's only seeing this, but I'm actually on the curve here. So if I do a design, and we actually wind up here, I can come in, if I have my system curve, I can come in and say, let's trim this impeller to 10.1. Now my system curve is right where my new impeller cut is. I'm not producing all this extra horsepower. I'm down in this horsepower range. I'm below 20 horse now. If I'm full impeller, I'm at 25 horse. If I trim the impeller, I'm less than 20. I'm saving energy. And this is what VFD.
Trimming is this way?
Yeah, you just cut an inch off. This one says 10.8. This one was right here. I can trim it down to 10.
Smaller OD.
Yeah.
Less horsepower. I'm saving energy by doing it. Okay? But a lot of people, you know, they don't realize like this was original design. They gave us this impeller, but in reality, this is what we had. We're actually, for the flow we need, we have to be way here, since we could trim that impeller, but we're going to operate here. And when they talk about non-overloading throughout the curve, you hear this all the time. See, this is 30 horse here. If I go out my whole impeller curve, I have to use a 40 horse here per se, just by this curve. Because if I let this pump go, if my design's off like this, well, let's say my design's way off, my curve's here, I can get out here in the curve and overload. But if I plot my system curve, I can avoid that and not have to do that. This is a variable speed curve. Now, what a variable speed curve does is a very VFD is actually a variable frequency drive. When it takes and it makes a sawtooth wave, and typical HVAC, we don't go below 20 or 30 hertz because we need that much energy to turn the impeller to start it. If we go too low, there's not enough power, the pump will stop and trip. So these are my impeller curves for my different frequencies. So 60 hertz, I'm at 1760. As I turn that down to 50 hertz, 40 hertz, 30 hertz, I'm going to these different speeds. Remember the other infinity curve, it tells you the speed varies. You can use that to calculate what speed you need. And here's our system curve. So as I back my speed down, my flow is going to actually reduce and walk right up and down this system curve line. At this RPM, I'm going to have this flow. At this RPM, I'm going to have that flow, 1760. Everybody follow that? So it's like trimming the impeller. It's like we did before, except we're just slowing it down and speeding it up. So the speed varies directly to it.
Those purple numbers are the flows?
Speed, RPM.
RPM.
And those, and if you take a 60 horse motor, go 0 to 60, it's 100% correlates to the speed. So at 30 hertz, which is 50%, I'll be half of 1760 or half of 1160 or half of 3500. Okay. Okay, this is important too. When we're doing pumps in parallel, pumps in series always stack the head, just like our vertical turbine and added head. Centrifugal pumps, you can deadhead. Positive displacement pumps, you cannot do that. They will blow themselves up. I can take this pump It's a typical pump like this impeller, throttle it to nothing and let it spin. It will develop heat over time, it could damage it, but for small times, it's just gonna slip, it's just gonna sit there and keep spinning. But when we make a series selection, every pump will add head, the flow will be constant, it's like an electrical circuit. Parallel versus series, series, the voltage stacks, parallel, you have the same flow, or split the flow, and have the same head. But when you make a pump selection in a parallel, a lot of people think I wrote an article for plumbing engineering quite a few years ago. People always say, well, I need more flow. Let's just put another pump in. Well, it doesn't work that way because this varies as the flow of the head, remember? So if I double my flow, what's going to happen to my head? It's going to go up to the square. The pump no longer has enough head to get. So if I make this selection, this is my original pump. Right here was my selection. Here's my system curve I laid in. What you do is you take this impeller curve, and to draw this second curve, all you do is say, okay, I've got, what is that, 88 feet ahead at 300. So I go out here and put a mark at 88 at 6. And I come back here and say, okay, I got 600, and I go out here and put a mark at 12. I come here and say, I got a mark here at 900, I go out here and put a mark at 1800. You can draw that second curve in. And what you do is once you lay your system curve in, here's my operation with one pump. I'm at 900 GPM almost. Here's where I'm going to get it 2 pumps. 2 pumps, I only gain 100 GPM.
Right.
But what,
If the head stayed the same.
well, no, it's based on, that's what I'm based on. I'm saying, but don't, based on the same head, yes. But my point is they don't double. If you double the pump, you're not going to double the flow because the head is the same, and because the head went up now. But I'm limited about that head increase. I'm only, and what will happen though is when I go to 2 pumps from this point, whatever this point is, let's say it's 1,000, they'll split and share at 500 each. They'll each share what we're pumping, but they won't. I can't come in here and say I want 1,800 GPM, put another pump in. No, I put another pump in. I just spent $4,000 for a new pump, and I gained 100 GPM.
But if you went double all your pipe sizes, and you probably.
Well, you could change your pipe size,
Whatever horsepower, the head back to where it
You
originally.
can do a lot of other things, but with our system, we have to be on this system curve. We didn't order it. This is what's limiting us for the increase. Nobody follow that? This okay? Nobody falling asleep? Am I too boring? And here's another curve like we talked about. If you have a very, very flat curve, and it's not too flat, but here's our original system curve. Here's our selection again. We did the second curve just by doubling this out. Here's what I'm going to get by picking up the 7 pump. 200 GPM is all we picked up. The steeper the curve is, the more we're going to get. Because here, this one, see, it's a steeper curve. We picked up a lot more flow because this curve is, we're sending it out. You got to be careful when you do this. If your new system curve looks like this, if it doesn't touch the original pump curve like this is, this pump would kick from parallel. Guess what's going to happen? The single pump's going to try to run on its old system curve here, and it can't get there from here. This is our new system curve with the full flow we're doing. This pump is no good for that selection. This has to cross. So if this one falls off, I could be on the operating point.
So it stops where it says P1, P2 on the left. It does not go to the right.
Well, this is one pump individually.
Yes.
This is 2 pumps together.
Can I put a line from P1, the left, P1, P2 down to the other line, or that doesn't exist?
I'm not quite following.
If I want to extend that line, and that doesn't exist below.
No,
P1,
no, that's my operating cutoff for
There's
that
no
pump.
such thing.
No, that pump is
Doesn't
tested.
exist.
A lot of reasons, and that's one thing I forgot to discuss. Well, we're going to get into it. I didn't forget to discuss it. NPSH comes into play there. Not get into that.
All right.
And again,
Can you back up 1 second?
yes, sir.
Just for clarification purposes, your left-hand P1, P2 cutoff is what, 850 gallons there? Somewhere in that neighborhood?
Correct.
That's where it's gonna stop. You're still gonna pump the 850,
Correct.
and it's not gonna go any higher than that. at 50 foot ahead.
But if I go into parallel, I'm good, but this is a new system curve, just ignore it.
Understood.
But with my new flow curve, with my new flow, I can't get there from here. So,
Non-existent.
and you gotta be careful about that. When we do pump parallel selections, we look for that. We say, what happens if one pump trips? Whoops, no good. I can't get there from here. Make another selection and we find one that meets it all. This is just a kind of, here's a selection. Now, we have 400 at 40. If I take a reading of 40 on here, and if this is my impeller, I'm not going to go out this way. For example, my next slide. A lot of people take a pump curve and they just go, oh, I'm at 40 feet ahead. This is where I'm going to operate. I'm at 40 feet. No, you have to have the system curve. I'm operating on the system, not out here. I can't come guess that way. I have to know what, I have to have an operating point to lay this curve to find out where I'm really in. I can't just arbitrarily pick and say, well, I have this impeller. What does it matter? The curve's back here. I can't get there from here again. If this one, let's say we need more horsepower, we need more flow. We want to evaluate this pump. When I come in here at 440, I use my affinity laws. I say, okay, we want to go out to 800 GPM. Well, look, if I had this pump, if I put a 12.75 inch impeller with a 50 horse motor, it might do it. But from where I am here, this is a true point. I can't. This pump's no good for that. I'm only going to get 800 and 150 feet. I can't get 800 GPM out of this. This is the most flow I'd ever get. If I change it to a max impeller, put a new impeller, big motor on it, this is the best that I can't get there from here with this pump. I got to change the pump. Are you following that? Make sense? Cavitation. This is a big thing. This comes into play more and more on my steam system, high temperature systems. I'll explain why in a second. This is the NPSHA calculation. On every pump curve, see these numbers up here? This is called net positive suction feet required. Every pump, from me, take your duty point, let's say this is your duty point, I come up here, okay, I need 6 feet. Net positive suction head based on HA, which is atmospheric pressure, plus or minus system washes, plus or minus the vapor pressure of water. If you look at a steam tape, 60-degree water, I might have 2 feet for a vapor the vaporization pressure. But I get up to 212 degrees, what happens to that term? I'm getting closer and closer to boiling. Now we start at 32 feet from atmosphere. Well, in a chilled water system, I'm at 40. This term, 2 doesn't make much difference. Condensate system, I've got 32 here, minus 31, and I need 6. Ooh, so this starts at, basically 32.7, PSI, atmospheric, plus or minus whatever friction losses you got coming in the pump.
That's minimum required pressure at the suction of the pump.
And you want to add 5 feet to it. At that, if you're right at that, it wants to cavitate. And what that means is I always hear in the field, cavitating is air. No, air doesn't do this. This is a severely cavitated impeller. This is what you get.
Some damage.
Be careful, it's very short. What happens is when I do get this HA term, my required is 6 and I only have 2. What happens is, you do remember in high school you used to do, everybody saying it, you put water in a vacuum chamber at room temperature, what happens? It boils. You can't cook in it. It's 80-degree water, but it's boiling. All that means is boiling is it just changing from liquid to vapor state.
What happens for 100 of atmospheric pressure? It's way down.
Exactly. But what will happen in the eye of your impeller, when you look at your impeller here, as the water enters the veins of the impeller, it's under high pressure. When it goes through the veins of the impeller, it reduces pressure. It speeds up as the Bernoulli equation. I have pressure here and the velocity, my velocity goes up, my pressure falls. Well, now we're in our vacuum chamber. what's happening to our water in the eye of that impeller. I don't have enough positive pressure there, it boils. And when it boils down, there are these little steam bubbles. Now the steam bubbles travel out the vein, hit high pressure, guess what happens to them? They collapse, and they do that. It will destroy an impeller. Tommy knows on our old ship, we had the high pressure turbine, low pressure turbine. I don't know if anybody for the video, we served on the same warship together at different times, but under the main condenser, the two condenser pumps sat there and ran at the same speed all the time. No level controls whatsoever. What happened is they designed these impellers and built them to cavitate. They were built out of titanium or gold or whatever the heck they were made out of, and they run all the time. And as your cavitation goes up, and your MPSH required gets exceeded, your pumping efficiency falls off. You can do a calculation. Okay, I'm 5 feet over it. I'm at 100%. If I get -4, I'm at 0 pumping. And that's how these pumps work. They're well filled up. Pressure went up in the stacked water, 2.31 per every feet of elevation. They get positive suction again. They pump. And they got so low, they start cavitating again. And they pump efficiency fall off. Brilliant, no level control. Just let it run all the time. It'll pump when it needs to. But you had to handle the cavitation. Okay, we talked about these already. This is the net positive required. What's available. This has to exceed 5 feet. Keep you out of trouble. That's 5 feet right here. You know, your vapor pressure. Remember I talked about that vapor pressure turn, HA. The 212, it's 32 feet. I'm at 0. I lost all my first term. It's gone. Now I'm minus. You know, that's why it's hard to pump it full pressure. Any questions on that?
I got a question.
Yes, sir.
Impeller.
Yes, sir.
That's a dual inlet, right?
No.
No.
Oh wait, yes it is. That's off of what case pump? Yeah, but
Why would it just cavitate on one side?
I have no idea. I don't know why I did that, but that
Could
is
have made something up.
that's out of a horizontal split case pump. That's the double the suction I was talking about. It is. I don't know why. No idea. But it didn't like it.
He spent days with a drum up one.
Sandpaper.
Yeah.
Very sure.
On there.
This is just another term to show you. Here's your required NPSH. So if I'm here, I come up here, I read my NPSH requirement. And I have to, my available has to exceed my required by 5 feet. This comes into play a lot. Closed hydronic system is not a big deal. Because remember our vapor pressure, that first term, the atmosphere. Well, if I have an open cooling tower sump, I'm using atmosphere. If I got a hydronic closed system or closed chilled water system, I'm putting 60 pounds or 40 pounds or 30 pounds of fill pressure on top of it. So now I've got to exhaust 20 pounds of fill pressure, 34.7 feet, or 12 PSI plus the 30. You'll never cavitate. But if I'm in an open loop system where I'm just using atmosphere, all I have is the pressure of atmosphere. Now we got to really be careful. If I've got a cooling tower that's 6 feet below, you know, you have your NA, your pressure minus your friction, plus or minus your elevation, plus or minus your vapor pressure. That tower is 8 feet down. I have to lift that. That's going against my NPSH.
So that positive suction head on there, that's temperature specifically you're working through it, right? And you have different charts for those for different
Correct.
temperatures.
Yeah, because if you notice when we do these, you know, well, it's not so much difference in temperature. What will change in your NPSH equation? Here's the equation right here again. This is atmosphere. So like I said, in a closed loop, I have atmosphere plus fill pressure. That's what I'm starting with. If I have an open cooling tower, all I have is 14.7 PSI, or 33 feet ahead. Plus or minus any elevations I have. The tower's 20 feet up, that's giving me good. If I'm lifting 6 feet, it's going the other way. Plus or minus my frictional losses, minus my vapor pressure. Again, heating system, boiler, where it's open to the atmosphere, 200 degree, we got a problem. Chilled water, closed loop, no big deal. Heating, this number gets real big, but I've got atmosphere plus 30 pounds.
So where does 32 come from?
Atmosphere, 14.7 PSI. 1 PSI is 2.31 feet of head.
14.7 times.
So you multiply 14.7 times 2.31. And if you ever figure in a pump in pressure, you figure pump head, 231 feet of head divided by 2.31 would be 100 pounds per square inch. You get down 2,310 feet in the ocean, divided by 2.31, you got 1,000 PSI. And it doesn't matter, a lot of people have the hard concept too. What's the pressure of, if I have a 100-foot straw, or I'm 100 foot down in the bottom of Lake Erie, which has more pressure? At the bottom of the, I got all this water there. What's the difference in pressure? None. They're both the same pressure, because it's in pounds per square inch.
43 point something.
There's more pressure in the big. You've got to multiply the surface area of the lake. But that absolute pressure at the bottom of that lake is
Per square inch.
14.7 PSI for the atmosphere, plus my depth. Is what I'm gonna read at the bottom of the straw or the bottom of the lake. It's gonna be the same as it's per square inch. Now, if I do the surface area of the lake, obviously there's a lot more weight there, but people have a hard time getting that concept. Okay, this is another thing. Remember we talked about the affinity laws? Here's a, 4-pole motor, 1760s, 234, 1160. This is a 1750 impeller, like this one is. The equivalent impeller for a 3500 would be this size. They get much smaller. They're spinning faster than noise. Okay, that RPM, you're getting your energy from the speed versus the impeller weighs less.
Is noise the only detriment?
What's that?
Is noise the only?
Pretty much. Well, but the problem is, in the higher I go in speed, it affects my NPSH. It's needs more NPSH for 3600, it drops for 1760. And if I do a lot of big towers that I do have to lift, I'll lift at 1160 because the NPSH requirements for that. So they're not churning as much. So you get a lot better net positive suction performance. And those are all calculated on your curves. You see it. Any questions? I'll come back to this. I wanted to talk about the replay. This is the new rate. I talked about our ECM pumps. A lot of the small pumps have this self-sensing. A lot of the new commercial pumps have this. These are self-balancing pumps. And the way they work, your drive will tell you what flow and head you're at. You start these, there's no DP. Normally in a VFD system, I've got a DP 2/3 of the way out in the system set at 3 or 4 PSI. As my 2 and 3 ways kick in and out, I'm changing the flow of my system, the VFDs are ramping up and down. But I have to have a control system that looks at this DP and samples it every 10 seconds. Way out, I got 100 feet of wire out there, blah, blah. These do away with all that. Magic. And what they do at the factory, they take a specific pump and they actually plot every impeller diameter in the computer on this pump. So it knows specifically at 100 GPM, I'm at 35 feet ahead, 50 I'm here, or so on and so forth. All that data is put in the computer. It's all in that drive. When you see a self-balancing curve, this is your performance area. You no longer look at impellers. As long as I'm in this window, my pump will handle whatever set point is in here. Okay? What happens is,
How does it sense it? Is it like through motor current, torque?
no, it actually just uses the yeah, well, it's a combination of that, yes. And that's how it knows where it is in the system. But what it does is it actually knows when you put in your head, you take a reading on the system. I said, okay, I've got, remember we fixed point in the system. Then I can make my system curve, right? Now I've got all these data points in here. I can go through and say, boom, 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 boom.
Don't do it.
We'll get back there eventually. Okay, so like I said, we have this system curve, but I know these impellers. I can say this impeller's here, this impeller's here, this impeller's here. Now I've got defined points where I know I have to be. And when we go in the field, we'll go in and actually take a head measurement. We'll guess at it, set it, then we'll go out in the field, take a real reading, and then change the programming, so it's running dead on that system curve. Okay,
Jeff, how is that temperature compensated?
what's that?
How's the curve temperature compensated?
Temperature.
Oh, temperature. Well, it's just based on flow and head. I don't think the temperature, it's so minor, viscosity change with temperature, it's really not gonna affect. Now, the liquid you put it in will change it, you know, because now we really have to worry about viscosity, because that will change my curve. But for water, it's so minor between, you know, it's so viscosity changes, specific gravity still as well. Everybody understand what specific gravity is? It's the comparison to
The density of
water, huh?
density of the water.
Density of the water, it's the density of the liquid compared to the density of water. The specific gravity of water is one. Okay,
High definition.
what's it? Yes. So here we have the design operating point. We put this system in. We programmed it for this, but we're actually out here. I can go in and tell the program, hey, this is where I'm at. I'm on this curve. Run these data points on it. That's how it knows exactly where it is. In the old days, to make this correction, remember when I talked about what I do? Throttle the funnel. What am I doing by doing that? Adding head. Okay, now I'm turning more speed, I'm throttling off that valve's dropping that head, I'm paying money for something.
But
I'm
you're
just
wasting energy on the motor.
Whereas the self-sensing, it's gonna shift its curve back up where it wants to be.
Slows it down.
Slows it
saves
down,
energy,
you're saving the energy.
and puts you on the spot.
And the way they'll work is, as the system flow changes up and down the system curve, the pump will actually step down. It'll step curve to curve to curve to curve till it gets where it knows it needs to be. Pretty neat concept. And it's getting more and more popular. How much time do we got left?
1 minute or half hour.
Anybody have any questions on pumps or anything?
With the,
What were those pictures you went by really fast?
We're gonna come the other way.
with the VFDs, do they have like a limit in them to stop them rotating, like stopping them from spinning too fast?
No, well, they're all limited, typically at 60 hertz. Yeah, there's a limit in them to 60 hertz, and when we program our drives, you know, they go 0 to 60, but we'll put the low end, like when they ramp up, we'll typically want to ramp up in 10 seconds, and our minimum speed, whether it's needed or not, it goes to 20 or 30 hertz automatic. They just jump right through it. But you can get critical speeds in there and it can really mess with the pump, so typically.
So you can run a, VFDs at up to double the 60 cycles to 120 cycles.
Well, you can, some of them allow you to go a percentage over. I don't like doing that.
Yeah.
If I'm gonna do that, that means I need more horsepower that's designed to pump and get everything working on the parameters.
Infinity rules only work up to exceed ideal blade speed, right?
Pardon?
Tip speed, the tip speed on the outside of the impeller. I mean,
Well, 17
you
seconds.
can't keep doubling the speed of it
Right.
indefinitely and doubling your flow.
No, eventually it's gonna start to malperform.
Right, it just turns into a mixer.
Exactly. So, but I'm saying we're limited 60 hertz. That's usually what we try to stay. Okay, expansion tank. Well, I forgot to mention, this is a really important equation. He was bringing this one up earlier. This is why hydronics, I love them, plus or minus 50%. And a lot of people don't get that. Your BTUs are equal to your GPM times 500 times your temperature difference. We typically design for 20 or 30 degree delta. 20 is pretty standard. The beauty of hydronics is most hydronic fan coils, fin tube, whatever you want, are designed to run between like 3 feet per second velocity to 8 feet per second velocity. As long as I stay in that range, the unit's going to perform correctly. The beauty of this, let's say we design it and whoops, I did my head count wrong. Instead of, you know, I wanted 10 GPM here times 20, you know, that's 200 times 5, that's, you know, 10,000. Okay, whoops, I goofed, I don't have 10,000 because now my flow's down because my head was too high. But the beauty is the delta T will drop and make up the difference, follow me? If this is inversely proportional. GPM doubles. Right, so even though I don't have
The
my,
higher the TF, so
I'm lower in flow, but as long as I'm in that range, okay, drop half my flow, my temperature difference went up by 2. The guy at the end goes, I got 10,000 BTUs, 20-degree delta T. Well, I up the flow, the temperature delta T goes down, oh, I got 10,000 BTUs, I'm good. You know, it's plus or minus 50%. And nobody does the difference, you know. Understand that concept? Okay, this is a rule of thumb we use a lot of times. People will call us and say, hey, I need a new expansion tank. All I have is a plain steel tank. Okay, I can estimate the volume in that plain steel tank. Or I'll say, well, we don't know how many expansion tanks are really sized by system volume. But this rule of thumb comes in very handy. If I have a boiler system, I can take BTUs of the boiler, divide by 15,000. If I have a 12 to 20 PSI fill system, that'll give me the full acceptance of the tank. I can go into my chart. There's 2 different kinds of expansion tanks. We'll get that in a minute. This is a full acceptance. And I can pick a tank, and I've never had one not be right. So if you don't know what your system volume is, you can guess at it. You know, just by taking your BTUs divided by 50,000 times a 5.5.
so that's assuming that somebody sized the boiler.
Well, I understand if you have an existing system working for 20 years, and if you take a plain steel tank in the system instead of a bladder, get rid of this 5.5, just divide by 15,000, that'll tell me the full acceptance of my bladder tank also. If I take, you know, it just happens to all work out perfect. And plain steel tanks are the atmospheric ones. They got the gauge glass in the end and tank full. Those are filled with atmospheric pressure. 12 pounds of fill compresses the tank. You lose half your tank up front. Plain steel tanks are twice as big as a bladder tank. In a bladder type tank, I have a bladder, the water's in the bladder, and I put an air charge around the outside. So instead of having atmospheric air around it, I've got 50 pounds of air around it. Whatever my fill pressure is what you want your air charge to be. And then they make a partial acceptance and a full acceptance. The full acceptance, the bladder mirrors the entire tank. The partial acceptance has a little bag hanging in the tank. I might have a 20-gallon bag with a 50-gallon tank. If I have a full acceptance tank, 50-gallon tank is a 50-gallon bladder. The difference is this price. That big bladder is a lot more expensive than that little bladder. And that's what I'm talking about. When you have the full bladder that mirrors the complete pattern of the tank, then you can use this rule.
So the rubber diaphragm has water in it, the air is the
Outside.
around the tank.
And the way they work is the reason you need that air charge. If I have a bladder type tank, the bladder's collapsed, there's nothing in it. If I don't have an air charge in that tank, I put 20 pounds of fill pressure on it, what happens to my tank?
It's already full.
You lose 2/3 of your tank, it fills up till it's like a plain steel tank now. But if I put a 20-pound air charge in there and put 20 pounds on the tank, guess what? It can't fill up. Now I start heating, the water migrates in, and this is another big misconception. I get so many, I just had this happen not too long
You
ago.
gotta put a charge on the bladder or against it first before you put the water in.
Correct. And you want to
Otherwise,
equal whatever your cold iron fill pressure. Equal your cold iron fill pressure.
Because if you don't, then you can't put it in after.
Well, you can put in, but you lift the relief off, so I don't know how much expansion volume, I lost it all one fill when it's full of water, I didn't need. What was I going, oh, they called me last week on this stuff. So many people think, well, I got a 15-pound fill. I got 100-pound relief. Oh, your expansion tank's not working. Why? Oh, we're at 200-degree water temp. I got 100 pounds in my system now. We started at 15. I'll say, what's your relief valve setting? 125. Okay, you're good. It's a 150-pound working system. We size expansion tanks based on fill temperature, max temperature, system volume, starting pressure, and relief valve setting. And we always size up to 5 pounds below relief valve setting. That system is going to go up in pressure regardless. If you want a 20-pound fill pressure and want it to stay at 20 where you expand all that water, your expansion tank's the size of this room. It's going to be huge. It's going to cost you $100,000. I got a 150-pound system. My fan coils are rated for 200. My fin tube's rated for 400. My valves are rated for 400. We're at 100 pounds. So, you know, and then when the system backs down in temperature, guess what? The water's going to creep down. That pressure in the tank's going to push the water back in the system. When I get back down to fill pressure, my system's going to be back to fill system pressure in at 15 to 20 pounds. But it's okay to let it go up. You don't have an issue until we lift release valves. And a lot of times if you have a plain steel tank, because there is no bladder, the water and air is touching each other. That's so I got 14 pounds of air in and I put 40 pounds of pressure on it, tank's half full. Over time, that water will dissolve in the air. And it'll leach up and leach up and leach up, and I'm losing expansion volume. So eventually one day you fire, guess what? I don't have no expansion tank. What's going to happen? I exceed the pressure of the relief valve. So if you ever get a relief valve pop, first thing to look at expansion tank. Look at my filter. Somebody screw with that. No, that's still good. Plain steel tank. Look at the sight glass. If it's full, isolate the tank, dump it, realign it, you're good. Bladder type tank. Take a little pen, open that up. You spit water out of there, guess what?
The bladder's got a hole.
Your bladder's broken. If I don't have my bladder or my air charge, what's wrong? Some of the tanks, like everybody makes a dull and gossip, we all do. On my CX tank, it's a diaphragm. We'll get into that in a second. And then you have the bladder tanks. But it's water. I run into this all the time. People, or for example, they'll go, no water, but no air. What? A bladder type tank. They're lifting a release valve. But they push the valve that they don't get any water out, but they're not getting any air either. What did we originally have in that tank when we started? Air. 50 pounds of air. I got no air. Guess what?
You didn't lost the shirt.
So how do you fix it?
You hope you can change the little Schrader, if that's all it is.
No. There's no air. The air is weaked out over time.
Yeah, the
What
Schrader
happens
might be
if
bad.
you throw a car tire out in your yard 5 years later? What's it look like?
Flat,
Flat. Why?
leak through the sidewalk.
Same thing with bladder type tanks. We recommend to check them once a year. Isolate them, drain the water off. A lot of times we're gonna recommend, we make like a ball valve with a hose end bib on it. On your expansion tank, when you make your connection, it's got a union, ball valve, and a hose end drain. And the hose end drains below the ball valve. Isolate the ball valve, open that hose end drain, let's any pressure come out. When I go to fill that tank, I want it open to atmosphere when I do it. Now I put my air compressor on there, I'm pumping air in there, what's gonna happen to the water in that tank? Now I've got nothing but air in there, realign the ball valve, close the drain, reopen the system, we're happy again. They will waterlog if you lose your air charge, and they will lose the air charge over time. Why? Who knows? But it's just like a car tire. Eventually, that's why we recommend, but you need to check them without the system pressure. I see a lot of guys go up, oh, there's 80 pounds in there. Oh, the system's at 80 pounds. You need to isolate it, open it, and see how much air we have in there. If we're 20 pounds of fill, you only have 10. Guess what? You need 10 more pounds of air. Fill it, realign it. Everybody's happy. But you're right. You hit that Schrader, you get water, busted bladder. And there's all sorts of other tappings on tanks. Don't ever take those out. People do it all the time.
Don't have to take.
There's an open end toxic bladder on it. People, especially, they'll get a broken bladder. And the bladder's full of water.
Hardest thing to pull out of the tank.
They'll take the plug out of the bottom with the pulls up here. I got this big rubber bladder full of water. Take that plug out all you want. Guess what? It's still full of water. So just use your air pressure to push it out. Make sense? Okay, these are examples. This is your plain steel gauge glass. Like I said, atmosphere. So when you first put pressure on this, it's going to fill halfway up. Your gauge glass is going to compress that 14 to 20 psi and stop. And eventually it's going to waterload. You open the drain, let the air back in, realign it. This is a CX series. This is a diaphragm tank, and these are a bladder tank and full bladder tank. I'll go through it. You see the bladder here. Here's your gauge glass. It's okay for it to be half full. It's going to be half full. It's never going to be empty because if I have 20 pounds of fill on it, 14 pounds of air in there, it's gonna have compression. That's why it's called a compression. Just a note, anytime you do an air separator, it always goes with the pump suction. We show it here. Here's your pump suction, this is your air separator. This is also where your expansion tank ties in. If you have a plain steel expansion tank, you want the air relief on the top of the tank to be piped back to the tank. Any air I remove from the system, I want to put back in my bladder tank. I want to recover it. When I have a bladder type tank here, I want to put an air vent here, and vent the air off. I don't want it going to the bladder tank. I don't want air in that bladder. I want it on the outside, not on the inside. Okay. So this is called the point of no pressure tank. This is where your makeup water is. Because when the pump comes on, if I put my tank over here, okay, I got 14.7 or 20 pounds of fill pressure here. I charge my tank to 14 over here. Guess what happens when the pump comes on? I got all this pump head. I just collapsed my tank even more. You always want it at the pump suction. There's your plain steel tank we were just talking about. There's about the difference from a bladder to a plain steel because you need that lead air at 14 pounds versus forced air. Much smaller tank. There's your water air cushion we just talked about. Okay, this is a diaphragm tank. See this little, it goes right in the middle of the tank.
How is it sealed in there? It's just,
I'm not sure. I've never cut one of those apart. But this is a throwaway tank.
it's not what.
You just throw it away. You can't replace it. It's junk. Less money up front, but you can't replace the bladder. But in reality, to replace the bladder, it's about 70% of the tank anyhow.
Yeah.
Plus your labor. So,
Yeah.
you know. But this bladder just goes up and down. Water's on the top, air's on the bottom, or vice versa. Well, it's the other way. No, the connection's at the bottom. So water's down here, air's up here. Bladder. It's like your rib cage bladder.
So the pressure on the top goes down into
It's on top of the bladder. Then the air pressure, the water comes up from the bottom.
it has like a dip tube.
Well, like this would have an air. So when the air is charged in here, this is going to expand down. And as the water comes in, it's going to compress that bladder, compress the air. And it's going to work just like when you're breathing your lungs. This is a partial expansion. This is the bladder that's in a CAX tank or a CBX tank. Everybody makes the same thing, Armstrong, anybody. There's a big tank. This is your bladder I was talking about, much smaller. When we size the system, it'll say, I need 22 gallons of acceptance and I need a 67-gallon tank to make that selection. It tells us we know what our expanded volume is. I can't exceed that. This is your CA tank. This is the one you can use that rule of thumb on. This bladder mirrors this entire tank. This is your gasket on top.
How do you get that thing out of it?
Chain fall. Choker. Lay the tank down, chain this. Hook the choker around this and crank it out. You put them in, they use a 2x4 to slide them in. And then once you get them in, you kind of cover it, put air in to expand the bladder. Not cover it, fully, just enough air to blow it out. And then put your lid back on and then charge it.
Try getting it out the water.
It's a lot of work. So a lot of times people just opt to buy a new tank. But these bladders, that is acceptable to replace. This you can replace, this you cannot. All of our tanks are 125 pound ASME codes. They're all ASME stamped and certified. Remember I said this is just telling you look at that acceptance volume versus the full volume. New side air separators in the world. Air inverts are becoming more and more prevalent. They have different materials inside. Spirotherm uses like brushes. We use these Paul rings. These new air separators will actually clean your system down to less than 20 micron. It acts as a filter, a micro condensing air separator. It'll actually take this much more out compared to a regular air separator. That's that chart showing. These Paul rings, all the fluid goes through there and it's changing directions. It's not going to dirty any air out. Very high efficiency, 125 pound ASME. We make them with a removable bladder or non-removable bladder. And you can just blow the dirt out of the bottom of them. You good on time? Sure. Any questions? Comments, purple stories? I just think that, can I get her again? I bore you to death? No. It's not the most exciting subject in the world. No bikinis.
One of the most requested subjects,
What's that?
pumps,
Oh, is it?
yes.
If you guys ever have any problems on a job, please don't hesitate to call us. We're pretty good guessers.
Your cell number or
What's that?
cell number? Oh, okay.
You're welcome to contact me anytime, whatever you need. I'm more than happy to help. That's the most fun. Like when I'm figuring out stuff. Oh, here's another good thing. I ran into this the other day, condensate units. Most people don't realize. Everybody understand what system balancing is. Balance will come in and they'll set all the boxes and they'll throw out the pumps to get the right GPMs. Condensate units need balance. Everybody thinks, oh, it's condensate unit, like their atmosphere, push it out in the system. The problem is I get so many systems out there that say I need 50 PSI of discharge. Now remember, I have my NPSH way the hell up there because it's 200 degree water, right? We got a real NPSH problem. The further I run out to a curve, what happens to the NPSH required? It goes way up. That's how that curve goes up. And they'll call me and say, oh, this pump isn't pumping, it's making noise. Blah, blah, blah. I said, you balance it. Always put a ball valve on the condensate pump or a glow valve on the district. Gate valves, you cannot balance. You have to have a valve you can sequence, not the gate, because so many closed, you just can't change the CD enough. So you need a globe or a ball. And the idea is, if they design that condensate pump to run at 50 PSI pressure, I just had this happen at SUMA this week. Oh, pump's not pumping, it's backing up. I said, was it balanced? No gauges, gate valves. Problem is, that's designed. Here on the curve, I only have 2 foot of NPSH. But that thing is trying to push against 10 pounds of head. I run way out here on the curve. Then NPSH goes through the roof. My pumpage efficiency does what? Falls off. Now I'm at 20% pump inefficiency. I'm damaging the impellers and I'm not pumping. But if I had a ball valve there, guess what? So I look back till that gauge goes to 50. Voila. Our pumping efficiency went to 100, just like our condenser used to do.
Never use a gate valve for throttling.
Never.
You wear it out.
Well, you can't even get by the time you get the opening small enough to create any back pressures.
Wire drawn, yeah.
What's that?
Wire drawn.
But a globe ball valve, I can turn that ball and change that CV. Or a globe valve, every turn I'm changing that CV just as minute. That gate valve, the first 80% of travel's doing nothing. My hole's still this big.
Ball
Now it's
valves
this big,
aren't-
now it's this big, now it's this big.
Ball valves aren't the best, I mean,
All of
40%
them
open, you're 90% full, but they're.
Not
they're
every manufacturer of balancing valves uses ball valves. Flow Design, Griswold, Bell Gossett, everybody's got ball valves. They do work really well. Butterflies work for balancing. You know, like Armstrong, they use the globes for their bigger ones. Then you have to count the turns. But a butterfly does just as well. You know, for example, Flow Design. The old Bell Gossett's the old take because you had that little whiz wheel. Because every time you turn that valve, you're changing the CV of the valve. I got to keep looking at my chart to change the CV. Where a lot of people like Bell Gossett's even went to it. Flow Design started it where we were at. They have a Venturian. These are Bernoulli's equation. Okay, if I'm at this point, I know I have this pressure at this flow. I choke it down. The velocity goes up, the pressure falls. So if I read that dimension, it's calibrated. I have a chart. If I get 2 inches here, I'm at 4 GPM. If I get 10 inches there, I'm at 15 GPM. I just throttle that ball valve to slow that velocity down to get that, and I'm done. I don't have to go back and forth. Okay, I turned it 20%, whiz wheel. Okay, turn it. Oh, now we're at 30%. Remember the whiz wheel. We just go, done. That's why the ball valves are much better.
Yeah, sewer department uses great big butterfly valves for the gully washers when they, so they don't overload the sewage
Oh, okay.
plants.
I just choke them back and
Yeah.
throttle
They just,
it. And the other thing, if you ever make a pump selection, yes, we end up throttling pumps. All pumps are usually oversized. The reason being, on 10% oversized, I can throttle. It's gonna work beautiful.
If you have enough,
20% undersized, guess what?
you
Just
got
go,
enough.
gotta buy another pump.
Well, when they, did the, at the Metro Park Zoo, they, where the rainforest, they were just last minute, they had all the shirt and tie guys and everything else, they come in when they put the thing on, it drenched every one of them till they badly, they throttled it way back.
Any questions, comments? Very good. Was it worthwhile?
Absolutely.
Thank you, Jeffrey.
You're welcome.
Appreciate it.
Okay.
Thank you.
Oh, Dan, what time is it?
NPSH.
No, we didn't. Oh, wow. What time we start? 6. 7 hours.